All right. We come to the conclusion of our annual event. For the past day and a half, we were talking GI. We talked about diagnostic criteria, rare entities, new entities, testing, genetic syndromes, molecular testing, what to say and what not to say in our reports, suggestive of. We talked about all that. And the event could not be complete without a look into the future and what the future is going to bring to us. And that is part of the tradition here at the University of Minnesota, where we believe in innovation, and informatics is part of the innovation. And we have a long history that, if you are not familiar with this book, I think this book is, we are very proud of it. It summarizes our 50 years of informatics in the University of Minnesota. So this is, we are very proud of this, part of us, part of who we are, and it was founded on the shoulders of giants. We have many giants here in the room. I always recall when I was leaving the University of Toronto, they asked me where you were going. I said, I'm going to the University of Minnesota. And they said, oh, you are going to the land of giants. Until today, I still see the giants. I see giants well established. I see giants in the making back there. And one of the giants we need to acknowledge today is Dr. Don Connelly, MD, PhD. Dr. Connelly was a professor in the Department of Pathology at the University of Minnesota, was the director of the Health Informatics Division. Dr. Connelly held many administrative and teaching positions. He led the whole organizations into informatics. He developed the first successful UMN laboratory information system in the Department of Laboratory Medicine. Through his efforts and the efforts of his dedicated faculty and staff, who were actually using their own computers back at the time and their own network. He taught, he published, and I think even our speaker today is going to speak more to that, to Dr. Connelly's effort. Residents from the University of Minnesota and from Mayo Clinic came to learn with Dr. Connelly. He was kind enough to share his information and teaching. Dr. Connelly is a fellow of the American College of Medical Informatics, a founding member of the American Medical Informatics Association, and was awarded a Lifetime Achievement Award from the Association of Pathology Informatics in 2003. And we can go on and on talking about Dr. Connelly and his contributions to the field of informatics and laboratory medicine. And to keep the tradition and to honor his work, the endowment for the Connelly Lectureship in Informatics was established, was sponsored by two other giants who are sitting here with us, Michael and Wendy Lougee. We know them very well. Wendy obviously is retired now, but she was the Dean of Libraries in the University of Minnesota. We all know Michael for his innovation and efforts in teaching informatics and many of the psychotherapy sessions he offered to some of our faculty. So thank you, Mike, for that. And today we are really proud to give the inaugural Donald Connelly Lectureship. So we are hoping that this lectureship will be part of our annual, hopefully, routine, and it will be an inspiration to some of the informatics giants in the making, sitting back there. Yes, I'm talking to you. You guys are going to take this and fly with it and learn from our teachers. And another giant sitting here, Dr. Balis, is a professor of informatics at the University of Michigan. He agreed to share with us this celebration, and we are honored to have you. Balis is the Director of Health Informatics Division at the University of Michigan. He is board certified in pathology informatics. He developed several innovative platforms in his field, and he held several grants. Currently, he's holding the NIH R01 grant to support his research initiatives. He runs a very successful fellowship in pathology informatics. He has more than 100 publications, and we are so honored to have Yul with us today. And Yul's name is going to appear as the first speaker in our lectureship, Connelly Pathology Informatics lectureship, on a plaque that will be displayed in the administrative office at the Department of Laboratory Medicine. So, Dr. Balis.
I guess it's okay for me to take my mask off. So thank you very much for that very warm welcome. I'm humbled by this plaque and by the opportunity to be here with you. And I also thank the association for the invitation this year. In the next few minutes, what I hope to share with you is kind of a potpourri of AI and machine learning, but from the prism of GI pathology. And at first I was a little hesitant to do that because I'm no longer signing out cases. When I moved to Michigan, I shifted to full-time informatics. But the reason I ended up feeling comfortable is when I was at MGH, I was full-time GI and full-time informatics. So I am a card-carrying GI pathologist, at least at one point in my life, and have sort of consumed from the fire hose, if you would. So, and a lot of the subjects of continued investigation in terms of basic science, image analytics, are still in GI pathology for me. So I hope you would consider me an honorary GI pathologist, if nothing more. This is a preface, and you've already heard about the accolades for Don. I just from a personal note, I met Don nearly 31 years ago in the CAP Informatics Committee, which at the time was a very vibrant group, it actually still is, in terms of identifying how computers could be more effectively leveraged for healthcare, for pathology workflow, for laboratory medicine workflow. And at that time, Don was one of the giants who have identified how you can effectively implement servers, laboratory information systems in support of these new multi-channel instruments at that time, which were generating more data than people were used to processing. And he was working very closely with, you set me up perfectly with this theme of giants. There were a number of giants at that time. There was Sid Goldblatt, who founded a number of companies, including SunQuest, which is still very successful as a company. Bruce Friedman. Bruce, if you're on the Zoom, hello, in Ann Arbor. Frank Elovich, who was also one of the chairs of the Informatics Committee at CAP, and Ray Aller. And actually, I'd be remiss if I didn't mention also Bill Dito, William Dito, who unfortunately you can't find a picture of him on the internet. Something strange about that, but many of you perhaps know of Bill or of his reputation. He was also one of the giants that really proselytized the notion that computers could be an effective, and now we recognize them as an indispensable tool in providing workflow and quality and automation and just ability to operate at scale, both in lab medicine and AP. And the thing which really excites me about this field right now is AP is discovering that we've had all along with our images and then tying the lab data, the clinical data, the molecular data, troves of information under our noses that we didn't know about, but it's reproducible, it's medically actionable, and you just have to extract it. It's kind of like, mining for gold. I should just mention that, as was already mentioned, Don, as you can see, was the second recipient of the Lifetime Achievement Award from the API. It was just very humbling for me to be in that light when I was awarded it in 2018. So that's another commonality that Don and I share. So moving forward to the presentation, kind of an ambitious thing to cover, but what I'd like to really outline is how AI and specifically machine learning will, not just for research purposes, but for clinical utility, make sign out more effective, faster, safer, easier, and really expand the potential of prediction. So in other words, identifying the biologic potential of disease. What is this lesion in this patient going to do in terms of its, is it going to metastasize? Is it going to recur? Is it going to stay senescent? And similarly, what are the theranostic potential? And in many cases, we're finding, and this is now emerging, you go to USCAP, there's all kinds of machine learning studies that are demonstrating this time and time again. There is encoded data in the morphology. If you combine it with the transcriptomic, genomic data, other types, just clinical lab data, other observations, which produces a reproducible signature of biologic potential. If nothing else, you remember today, just remember that anatomic pathology data, histology, is doubly important now that you can combine it with these other modalities of data together. So, 15, 20 years ago, those of you, for example, familiar with molecular, there was a cadre of molecular pathologists saying, oh, you AP people are going to just go away, right? We're going to put it all in test tubes, grind it up, and we won't need you. Well, you could immediately think there's a little problem there, right? What about anatomic frame of reference? Simple question. Is there tumor at the margin? Guess what? If you grind it all up and put it in a test tube, you're not going to be able to answer that. Anatomic frame of reference is kind of useful in many circumstances. You're not going to diagnose chronic cholecystitis with a molecular test tube, right? You're going to look at it. So the morphologic frame of reference, I think, is here to stay. And in tandem with that, and I'll get to that in a little bit, the need for an adult in the room, vis-a-vis a pathologist, to look at all these signals is going to stay. What we do as pathologists will absolutely change. We should expect that. We will need new skills, but what I don't think will change is the notion that there will be the specialty pathology using tools, perhaps more and more computational tools, to render diagnoses and biologic potential of disease. We're not going to be replaced, as some other specialties hypothesize. What will happen, of course, is what we do on a day-to-day basis will change. But I think the change will be for the better. And that's what I hope to show you. These tools are not meant to replace us. They're meant to make us better and meant to make the outcomes of our patients better. So, I hope at the end of this, you will see the excitement that I have for the specialty now, because this is really a renaissance period now that we can actually integrate multiple types of data with these tools, which are really in many ways no more than just elegant applications of statistics to the discovery of signals that have been there all along. So to do this, I'm going to go through very briefly just some of the high points of how machine learning is important for this. This is not a machine learning symposium by any stretch. There's not enough time to go through the field. It's a huge field in itself. And now I'll give you some observations of why we need special tools for pathologists that pathologists can use directly, as opposed to so-called big box models where you buy a commercial platform that does like a specific thing like HER2 or whatnot. There's a place for those, but I think there's also a place for tools where pathologists on the fly can generate computational pipelines to answer a new question that hasn't been posed before. And that's actually the focus of my lab group, is building algorithms that all the vendors have so far at least chosen to ignore, which is it's a more difficult problem, which is creating an on-demand real-time tool. So you're signing out a case and you see a morphology that is perhaps a bit novel or unusual, and you want to say, okay, I'm not going to spend 3 hours. I want the computer to spend 3 hours. Find me everything in this set of slides that looks like this weird thing. And maybe it's dirt, maybe it's an unusual cell type, but just at least let's look at a few more to get the variability. And right now, there's no tool that does that. And that type of solution now is emerging from multiple groups in the US and Europe. And it's worth pointing that out as a new opportunity. In tandem with that, these flexible tools, is the need for multi-axial analysis of data to look at the morphology, the omics, the clinical trajectory, and any other type of variable that might have a signal that when added together statistically equals a more profound or accurate prediction of biologic potential of disease. And we'll go through some examples of that. And finally, at the end, I'll showcase a couple examples that are coming from the Kidney Precision Medicine Project. So it's not GI, so you'll have to forgive me, but it is NIDDK, right? So that's kind of close cousin. But I do have a number of GI examples as well. So I think both of these are intended to underscore what the opportunity and potential are. And as one thing that I'm going to do near the very end that everybody tells you don't do because it ends up in disaster is a live demonstration of software that does really, but it'll work, trust me. Famous last words. And then some closing thoughts. So again, grounding this in the world of sign out. So again, I'm not trying to talk about theoretical things here, trying to look at the problems we face as pathologists and the ever increasing pressures of high volume combined with perhaps less staffing to address that volume. You know, when you're rushed, you know, what happens, right? You make mistakes, and this is what we're trying to avoid. So, you know, we look at the limitations. What we do now as pathologists, if we don't have computational support, which we largely don't do, because even with digital pathology, remote diagnosis, that's still looking at all the slides, right? And you're using the digital technology, at least as a first pass, just to be able to not use the slide, to be able to, let's say, be at home because of COVID or other realities and sign out your cases. That's still very powerful, but you're not fully utilizing the fact it's in a digital modality. So what we still do is screening. And if you could change that screening to directed review, and I'll mention this multiple times in the presentation, that lets you elevates your level of practice, your highest credentialed level. You're not just looking for stuff at this point. You're actually using your expertise to look at all the things that have been flagged for you and make a determination, up or down call. Is this what it is or not? And this is what I meant by the adult in the room. Algorithms often make incredibly unbelievable mistakes in the right edge condition that the original programmers didn't anticipate. The pathologist is there to make sure that the algorithm doesn't send out some incredibly wrong, you know, diagnosis or set of features. And that's not going to change for a while, because if you think about the practice of pathology, and I saw this every week at MGH, which has, you know, a very large volume, there isn't a week that goes by that some unusual combination of morphologic features that diagnoses are juxtaposed that's essentially never been reported before, never been reported that same way. And it always puzzled me. You know, you think about statistical tails. How can the statistical tail of variability in anatomic pathology be infinitely long? I don't know, but it is. And so you can't really anticipate a set of programmers in any, you know, programming AI group to anticipate all the edge conditions. At least I think not in our lifetimes. So another frustration or limitation, classification and prediction. We've done pretty good as a specialty in improving our kappa statistics for some diagnoses, but not all. And this is where the targeted and I think responsible use of AI and machine learning can help us, because there are things that computers do which is better than what a human can do in terms of finding features, quantifying the presence or quantity of the feature, or the count of the feature, mitotic figures, for example, and then giving a score that, if applied to like a larger population of cases or slides, will yield a much more tight and consistent result. The precision and accuracy slide that you saw earlier this morning, to have the high accuracy and high precision. And there are things that computer can do that can assist with that. The evolution of cases. And this is as much workflow as it is technology. Just having the priors conveniently available when you're signing out a current case. Sometimes you do, sometimes you don't. Sometimes you know where they are, but you're on the fence whether you need them, and you make a decision to not look at them because you're pretty sure, just from reading the prior report, that there's no change or there has been a change. How many of you are guilty of not pulling the priors when you think you might have to? Few hands out there. Quantization and quantification. Excuse me. My asthma's acting up. Just counting things, mitotic figures. GI is one of the specialties that enjoys that, right? 50 high power fields for GIST. How many of you did a GIST in the last month or so? You had to count a few mitotic figures. See, some hands are going up. How long did it take you? 10, 20 minutes. Was it fun? There you go. So if you could do that in like less than a minute, maybe 2, if you're really being careful. Would you like that? Okay. I'll show you that. And then thresholds for seeking consultation. I think one of the aspects of surgical pathology, which when you think in your mind that you've really arrived at what is competence, competence, I think in many ways is synonymous with modesty. Just knowing you know a lot, but you don't know everything. And when you see a case that your gut just tells you, this is one of those cases that just needs to be shown around, and you're comfortable showing it around, and you do. And that yields overall better quality reports. So from that vantage point of modesty, would any of you feel uncomfortable if an algorithm were working in parallel with what you're looking at and would simply flag a case that probably from statistics and the variables present would benefit from being shown around? Would you feel offended by that? No, it's not replacing you. It's actually helping you. It prevents obviously litigation, but helping the patient, get a diagnosis that probably merits more eyes looking at it if it's kind of one of these unusual diagnoses that merits greater expertise. And this is just maybe a subset of the list of things that just happen on a daily basis in sign out that could benefit from automation. So this is the vantage point, the prism from which I'm trying to show you some interesting technologies that are either arriving now or will be available within a 5-year period. So this is not hypothetical stuff. And one thing you can consider, as awful as this pandemic has been, specifically from the vantage point of pathology, since it's forced many of our peers to be off-site, it's forced us, right, to, as a conservative specialty, to at least consider using digital pathology for remote practice. And we found what? It works. We can do it. And we've made those arguments now to CLIA and other organizations so that the barriers from a regulatory perspective are not perhaps so onerous as they were just 2 years ago. So that's encouraging. So some general observations. AI is a very broad term. In the field of the analytics, most people refer to this as machine learning, which is using algorithms to look for specific signatures, physiologic states, or morphologies in the case of image analysis. And specifically, when you look at many of these algorithms, they're extensions of what we've been doing for many years with statistics. They're just more sophisticated applications of standard statistical rules. One of the key aspects of these applications is they operate in a high dimensional space. That sounds fancy, but it's really not. It's like, in other words, you don't have 2, 3 variables. Let's say you have 150 variables. And if you look at the variables as independent variables, you can model that as a 150 dimensional space. I don't know what a 150 dimensional space looks like. I know what a 2-dimensional space is, like a piece of paper, a plane, a 3-dimensional space of volume, 4-dimensional space, perhaps a family of volumes, a 5-dimensional space, maybe a plane, X and Y of volume. In 6-dimensional space would be a volume of volumes. After that, I kind of tune out. But the mathematics doesn't care. There are distances. And if you use mathematical spaces like that to say, how far is one object from another, we can see a distance of 2 points on a plane, distance of 2 points in a volume. It gets harder though when you talk about a hypersphere or a hypercube, tesseract, if you would. You can't do it, at least I can't. But that doesn't matter, the algorithms can. So a lot of the algorithms I'll be showing you are operating in what I call K space, where K is some big number. Doesn't matter how big, it's just bigger than we can visualize. And the tool basically helps us understand how close or how far apart these points are, these events. And if you have multiple events, do they cluster together in this high dimensional space, which is no different than points clustering together in a 3-dimensional space. It's a higher dimension. And the end of the day, you have these the same resultant metrics: closeness together of a cluster, and between any 2 events, independent events, how far are they? A geometric or Euclidean distance. And those are the concepts hold true regardless of how complex a dimensional space is. So there's some of the sobering realities that I think as data scientists we face, the thresholds of complexity of data. And if we look at this map, for example, let's see if this is working. My mouse back? here. If we look, for example, at a simple threshold, single analyte from a chemistry lab or a Chem 7, then we could get a chemistry and a CBC. And then we can get panels of data. It turns out the threshold where even someone with deep subject matter expertise can no longer extract all the actionable information is somewhere between 7 and 11 analytes. It's rather sobering. Doesn't mean we're bad cognitively, just we're not good at visualizing high dimensional data. So even for, extracting all the information from simple lab medicine outputs, chemistry panels, CBC, there's opportunities to use machine learning. And this is a lecture entirely apart from what I'm speaking on today, but we have a lab medicine computational unit where we result thiopurine analytes computation without doing any bench-based testing. And it's better than the Prometheus Labs test substantially. That's an example of extracting data out of a relatively low dimensional 29 variable system, CBC and a comprehensive chemistry. It gets worse though, as you go to higher and higher complexity, tissue microarrays, expression array data, single whole slide imaging data, and in libraries of whole slide images, or you add NGS panels, or at the top, populations of NGS panels in time series format, we hit another threshold, which is about 10 to the 10, 10 to the 11 data elements. And the reason this is important, and I'm sure none of us consider us in that realm, but this puts pathology and lab medicine squarely into the realm of being a supercomputing specialty. How many of you think of yourselves as a supercomputing data scientist? Okay, we got one of the first time. Excellent. So that we need to get more of you, right? Where have you been all these years? So this is the problem. We don't train. Even at Michigan, we haven't figured out how to get hours in. There's this huge competition, right, for hours, to contact hours with the residents and fellows. So we have some ability to do this with the informatics fellows, but not so much with the residents. And this is a problem. But I put this point up here just to underscore the fact that if it hasn't happened yet for the specialty at large, it will soon, especially as you go to using whole slide images in libraries. We are going to be curating between the whole slide images and the NGS data sets and the transcriptomics, which is going spatial, by the way. And I'll show you that at the end. We're going to have a situation where we have data for which we don't have the skills to be stewards. And if that happens, and we know exactly what the outcome is often, other individuals from other specialties, data sciences, machine learning, will step in and either try helping us or potentially taking the data over, where they just come over and say, we want your data. And I hate to pick on Google, but they're a great example of an institution that does this. They'll come in the spirit of partnership, and really what they want is your data. And I think that's unfortunate, because really the specialty should participate in the analysis of the data for which it already is generating. So I'll get off my soapbox on that. But I mean, this is a challenge for the specialty, how we generate enough of our peers who can participate actively in curating petascale data sets. So a simple example of machine learning, many of you seen this, as a high dimensional space. How does a neural network recognize handwriting? Well, if we look at a simple derivation, the U.S. Post Office did a number of years ago, chopping up individual numbers into 28 by 28 pixels. Well, that's a 28 by 28. If you look at the individual pixels as individual point events, that's a 28 squared dimensional space, where each one of these pixel values can be different from each other. And if you generate a neural network, at least initially, by chunking this into smaller groups, and you can identify edges and curves and features of the individual numbers, which then in turn, when they occur in patterns, can inform other layers of the network until you finally have a collage of the components. Like, for example, maybe the little arm of the 4 versus the vertical rise here and the vertical rise here. And all those together then create a unique signature, which can be further and further distilled through multiple layers of a convolutional neural network till you have, in this case, 10 outputs, 0 through 9. And it recognizes the most likely, not necessarily 100% guaranteed, but the most likely number to be given whatever the input variable is. Well, the problem if you apply this simple convolutional model to pathology excuse me, is that the world is not black and white. There's not just 10 diagnoses, right? There's probably infinitely many, but many, right? And so for one given organ system, let's say, gastric biopsy. Well, there's, antrum, fundus, whatnot. How many diagnoses can be generated from a gastric biopsy? That's a silly question, right? But so simple models like this don't work. At least they're not going to solve the whole universe of problems. You can create individual pipelines. And I think that's where eventually the field is going to be headed, that we have tools that operate in parallel with what we're doing, which is the routine histologic examination, that will flag things that fit a particular pattern. And there's no limit to the number of tools we can have operating in parallel. And these tools will generate statistical clusters. Here's an example for the numbers in a three-dimensional space where things cluster together, where if you create, in other words, spaces that localize a particular event to a manifold or cloud, where you say anything that occurs in this volumetric area is a 4, anything in this area is an 8, and this is a 5. And you create a boundary between those that has the highest specificity and sensitivity, then you have a classifier. Well, you can do that with histology. Is it 100% accurate? No, but it actually gives you, it's not just, is it yes or no, it gives you a likelihood ratio. So you could actually use tools like this, if carefully curated, to give you a differential diagnosis with an odds ratio or likelihood. And then once at least it's jogged your memory, then you can use it. For the example, let's say that you've identified adenocarcinoma in a biopsy, and you're happy with that, and you've probably done it correctly. But because of that psychology of having arrived upon the diagnosis, you miss the amyloid, because it's a second thing, it's a small finding. If somebody says, is there amyloid, you would look, and even without doing the Congo Reddit, because it was so exuberant, you'd find it right away. But you weren't looking for it. So because it's very hard to remind yourself to look at each and every case, okay, is there amyloid? Is there this? Is there that? And if you have an algorithm that running in parallel for amyloid, and it flags amyloid morphology, it's not saying there's amyloid. It's saying, look in this case, do you see it? That's the kind of error proofing or forcing function that these tools, I think, can provide to elevate our level of practice. Because if somebody's asking you, is there amyloid? That's a much different question than saying, here's a slide, what's in it? Right? So these are the kinds of tools I think will elevate our practice. And just to sort of wrap up on the mini course on machine learning, there's two modes. They're both valid for creating algorithms. There's supervised, where you already have an idea of the classes of features, and you're trying to train the algorithm to identify what are the classes when it sees a new untrained image. And so you're creating a support vector, which is a fancy way of saying a line between one cloud or one cluster and another, which optimizes sensitivity and specificity. You're creating this manifold. The supervision is the domain expertise that goes into the training set that says, okay, this is the initial training set where these X's represent things that I'm sure is this diagnosis. These O's are things that I'm sure are the other diagnosis. That's a supervised training model. In the unsupervised training model, you just basically say, here's a bunch of images. The convolutional neural network is tasked with finding how they're different in all sorts of ways. Sometimes it'll find ways that are different, that's things that you didn't want. For example, let's say you had a cohort of controls and malignant cases. And the algorithm is going to use anything present in an unsupervised model to figure out what's what. So let's say the malignant cases came from one histology lab that's hematoxylin is slightly darker than the benign cases. You could absolutely be assured the algorithm is going to say, oh, the darker cases, they're cancer. But that in other words, you've clustered them, but phenomenologically it may be incorrect. And this is why with unsupervised approaches, you have to be very careful. And this is why people talk about explainable AI, to go back and see why the algorithms are matching on with very high specificity or sensitivity. You may be fooled. So the take-home message is with any approach, whether it be supervised or especially unsupervised, if you're getting phenomenally high performance terms of your ROC curves and sensitivity and specificity, be very, very suspect that you're not actually detecting the signal of interest. You're looking at an anomaly that's biasing. So sample bias is an incredibly important aspect of machine learning that you have to stamp out to make sure that your algorithms are actually doing what you think they are. And in terms of the overall approach for making these algorithms, and this is a challenge for lab medicine, the idea is you engineer the features, whether it be supervised or unsupervised. You train the algorithm and you test them on an uninitiated cohort that the algorithm has never seen. You look and you deploy and you see how it succeeds or fails. And you learn from the failures by perhaps retraining on those events that failed, but may have unique features. And then you repeat the cycle. It's important, though, to recognize there's a challenge here from the perspective of clinical grade services. The machine learning model, you look at this, argues for making as many revisions as possible, iterations, to make it better and better and better. Because the more iterations you do, the better it gets. But similarly, if we're using these for clinical diagnostics, the same metric that we have for the lab medicine or any test, there needs to be validation documentation. This is still an aspect of machine learning and application to clinical medicine that's being worked out. What's the appropriate update rate and frequency that you do these things? Because you have to have at least some documentation that you validated it and you know it works to some minimum threshold of performance. But if you don't iterate, you'll never get better. I don't have an answer for you that, but I just point out that we have to enter into this at least somewhat cautiously initially so that we don't make a really bad initial mistake, thinking of the Gartner hype curve, that then jaundices people saying, oh, this is hype, you're just going to hurt people by applying these algorithms. So there's a need for being cautious in iterating through these algorithms so that we don't do something which ends up being completely wrong. And the good news is there is a large and growing portfolio of open source or relatively inexpensive tools. And even if there's a tool that costs money, there's typically an open source community that is incensed by that and is writing an open source package that's just as good. I mean, if you think of an example, Photoshop. For those institutions that have Photoshop, great, but it's expensive. But for those that don't, there's an open source project called GIMP. It's like 95% the functionality of Photoshop. Same thing applies to machine learning. There are many, many tools now that are completely free, Python libraries, for example, that work just as well as any of the commercial packages. In fact, many commercial packages are just wrappers around the open source libraries. So having some basic informatics training or someone in your group who has informatics training can be incredibly powerful for leveraging things without necessarily having to spend a lot of money, just knowing where the resources are and leveraging them locally. And then one final interesting comment about deep learning, not that they're bad or good, but they have an interesting property, which may be of interest to surgical pathology and anatomic pathology. Most of the traditional types of neural networks and machine learning have this unfortunate property of asymptotic plateau. As you throw more and more cases or instances at them, they get better for a while. And then they either get overtrained, even the curves can drop, or they plateau. So throwing more data at them, they don't get better. And this is a problem. And in 2006, it took a long time to percolate into healthcare. Hinton in Canada identified a targeted architecture of convolutional neural networks, deep networks, that as you put more and more cases or examples to them, they continue to get better and better and better. And so you've probably heard a lot in the literature or in the news about deep learning. This is why deep learning is so competitive and so compelling. Companies that, for example, like Google and OpenAI, which they've scoured the earth, absorbing all the data scientists they can who are experts in this, have found that appropriately implemented deep learning networks, as you throw more and more cases at them, get better and better. And that's in fact the exact type of algorithm that's being used for self-driving vehicles now. The input, of course, is all the scenery and visualization and LiDAR and other data telemetry that goes in from moving vehicles that makes these algorithms better and better. I don't know when I would be comfortable going in a self-driving car. I think there's still work to be done. But the parallel to surgical pathology is that even with a single slide, you have many, many, many fields of view, and GI is a great example. There are other organ systems like renal, that the anatomic structure is highly repetitive, right? You look at like epithelial surfaces, villi and crypts, reproductions of the same thematic element over and over and over again. And that represents a huge number of examples of either health or disease that can fuel these algorithms to converge more quickly on a universal or refined solution, which is correct. So this is one of the promises of the recent 10 or 15 years of machine learning, which has really fueled the accelerated discoveries, is these algorithms that actually can take advantage of the large number of instances of images or data points. So this non-asymptotic improvement is really important. So shifting gears slightly, the NIDDK Kidney Precision Medicine Project really is a wonderful exemplar of how you can take all different kinds of data and combine it with histology data. So this is really one of the unique aspects of this project, that the histology data is the center point from which the other classes of clinical data and molecular data emanate out. And that I think is somewhat unusual. The other thing unusual is that the patients or subjects are actually patients at the same time. So the project calls them participants, because the intent of the project is not only to find generalized knowledge, which is typically what a grant is for. In this case, is to find treatments or targets to help those particular individuals. And the reason that was deemed necessary is these very generous participants are allowing for the generation or extraction of research biopsies, renal biopsies that are not medically indicated. NIH has never done this before. And this took 2 years at the beginning of the grant to get this through all the IRBs to allow for research human biopsies, renal biopsies. So in having those biopsies, we're creating a tissue atlas and hoping to further define or characterize the subgroups. And that's for two particular disease entities, acute kidney injury and chronic kidney disease. And at this point, excuse me, we have established the atlas, and we're running on those biopsies, besides the image, quite a bit of tissue interrogation assays, which is generating the various transcriptomic and spatial data, but it's spatial transcriptomics. So in other words, for any given pixel location on a histology slide, we are now generating between, if we're doing like multiplex immunofluorescence, hundreds of 200 images in fluorescence signal, or if we're doing Visium 10x genomics platform, 2,000 to 3,000 transcriptomic signatures per histology location or region. And the pixel size is dropping now from 40 microns to 5 microns. So not quite a cell, but getting into the cellular range. And I'll show you at the very end some data that underscores what this means for potential discovery as well as diagnostics and pathology. So if we look at this from the prism of what historically an atlas meant, which is a book of pretty pictures, this is now transitioning to the notion, and again, this is for renal, but there's no reason why eventually this can't be for every organ system, certainly GI included, a histology atlas that ties that's better, to multiple classes of data. The match clinical content for that individual, the match morphologic content for the histology or maybe fluorescent images, and the match molecular content, with a distinct opportunity being to now carry out queries that start in the image space, in the anatomic pathology space. So you can find, for example, a single disease glomerulus, map that to other cases that have a similar morphology, and ask a simple question: what is their clinical trajectory? Simple statistical question. Patients like me, in other words. You can map it over to molecular content and look at the current molecular content and see if there are trends that are reproduced. In other words, does the morphology match with the molecular trajectory? Which means at some point when you've bridged them over statistically, you can use the morphology as a surrogate for much more complex subvisual information, which is molecular. And then finally, you can match them to the clinical trajectory, the biologic potential disease, for example, the number of months to the onset of renal failure in the case of cancer, recurrence or death, Kaplan-Meier curves, matching patients, so that it's possible now, and it's already been reported in the literature, that histology can predict recurrence for a number of tumors without even the molecular data. And when you add the molecular data, it's that much more powerful. So to accomplish all this, you need really a foundational model. You need to have your digital workflow in place. Fortunately, that's happening. You need to have quality systems. Anat Matabushi at Case Western recently published this year HistoQC. It's free. It needs a server and some system with memory and hardware to run. It will take the output of your scanning facility and flag those cases that are in need of revision from various artifacts, whether it be knife edge, chatter, overstaining, air bubbles, about 15 metrics of image quality. Because you really don't want to submit inferior images to your image analytics pipeline. Single features. Single features are useful from the image analytics pipeline, but really to get deep meaning out of an image, you need multiple features. And that's really the sweet spot. Generating as many features as possible to generate a multivariate signature where the pixels of an image become not color information, which is what they are now. There's basically each pixel is a red, green, blue value. Forget about that triplet. Each pixel then is now just a location in an image that gives you a biological context. What is this location's biological equivalence to base of membrane, or to being a nucleus, or being in like invasive? Every concept you can think of, there's no limit. Like this is a cell or a tumor border invasion pixel. When you have enough of those vectors and you do multivariate analysis, not only do you have an idea of what type of cell it is, but you have an idea of what the physiology is of that location without having to even add the omics data. When you add the omics data, it becomes even more powerful. And then finally, turnkey systems that theoretically are fully autonomous and will replace the pathologists. This is the thing I went on my rant on earlier. I mean, yes, it's a concept. I don't advocate for this. I don't think this is going to happen in our lifetime. All that will change is what we do as pathologists. We're not going away. So these full turnkey systems where you have a box that just signs out the slides, I don't see it. I just don't see it. So to get to this future state requires some sweat equity. We have to train the algorithms. Jeroen van der Laak, who gave the timely lecture a couple years ago at USCAP, had one slide. I'm still pestering him to share it with me, that had slave cave. How many of you remember that? That was his graduate students that circle things, or undergrads rather, spend all their hours circling things, creating ground truth maps, in this case of crypts. Could be kind of boring, but you need that kind of training set to generate algorithms. Similarly, if you're looking for a rare event, you need to give examples to algorithms so that the computer can look for similar things. The problem is if you give the task to a human to circle, just simple task of circling things, it turns out we're really bad at it. And I think this harks back to our experiences in preschool and kindergarten. There was always one child in the class who could do a really good job of staying in the lines, and everybody else are mere mortals, not so much, right? So I mean, I did this as an exercise, and I think I did a pretty bad job on this one. This is for illustrative purposes, though. But this is the kind of task that is often needed for training these algorithms in semi-supervised mode. Again, for fully supervised mode, you don't worry about that. You worry about whether it's actually locked in on a true structure or true feature. But in this case, where you know pretty much what the target morphology is, Gleason grades, for example, or malignant epithelial surface versus benign epithelial surface, that's where you need good training examples. And that's very tedious to generate. And these are tools in discovery mode that requires effort. But there's also another workflow, which is in I think, pathology sign out mode. If you're just looking for a structure, and just say, as an example, you've got weird mitotic figures, and you could use your big box software from a vendor that does this, but it's been trained on like the usual morphology of mitotic figures, and is not doing such a good job. So what you want is a tool that will look at the examples you've given it in this slide, in this preparation, and then extend that to the rest of the slide with extremely high precision. Doesn't exist yet. That's the kind of tool that needs to happen. So it's starting. So this is from Anant Matabushi's group. This is the quick annotator. It was just published this year. It lets you find structures that are similar to the predicates you provide. So basically, the things that are in, after you've given a few examples, things in magenta are the regions that have things that are candidates to what you've selected. However, it doesn't go as far as it needs to. I think they're working on the next generation. What it needs to do is not only find things that are candidates to what you've given as an example, but then classify them by looking at multiple variables, multiple features in parallel, and say, what is it? And if you carry out this to its logical extent or conclusion, you can literally define the biologic meaning of every pixel in a whole slide image. And like, well, why would you want to do that? Well, I asked that question a couple years ago, and at first it sounded silly, but then really what it allows you to do, you have to see the image first to answer the question why you'd want to do it. And the answer is because then it remaps the image, the histology, not in the framework of being a bunch of colors, which is what histology is, but in the framework of a biological map. And then, at least for me and the people on our team, we're now having to retrain ourselves. What do those maps mean, right? They're different than normal images. And so this is a discovery process, but I can see it pointing in directly in the not too distant future to being part of routine workflow. So these are further examples, for example, of the rapid annotator tool, identifying islands of cells in the magenta. But again, it's not going to the level of pixels. It's just general regions. And then once it gives you the regions, it doesn't subclassify them. So it's a good start. Conversely, what we've done with the vectorized identification of pre-screen regions algorithm, the Viper, is create a tool that can be used directly by pathologists. And this is not a commercial effort at all. This tool we're sharing with everybody. This is an academic venture. It's part of the KPMP NIDDK project. So the intent is to get this in many people's hands as possible, initially as a discovery tool, but we're hoping that we can show the utility for various types of clinical sign-out workflow as well. And it has three key thrusts. It has a built-in whole slide viewer for visualization. It's got a high-performance segmentation tool, like I showed earlier with the quick annotator, which is useful for generating annotated slides. But it has built-in analytics. So it actually will classify the entire surface area in terms of its biologic potential. And it operates at multiple length scales. So you can classify at low magnification, where you're looking at mesoscale structures, and then at the cellular and subcellular level. And what that actually looks like in a workflow, and this is the software I'll demonstrate. You start with an original whole slide image, and you take various tiles from it. You can't analyze the whole thing at once, nor would you want to. You sort of analyze it by feature of interest at a time and make a library of these tiles. So the original image then becomes a series of classifier vectors. Any one of these is not that interesting. I mean, it's somewhat interesting, but you're not going to use that to make a final classifier map. But for example, this one I can look at right away. The areas that are closest to white, this relatively bright cyan, tells me right away, this is a vector I was looking for the tubular nuclei of this renal biopsy. And you can see this line suggests that white, that this was a vector for basement membrane. This was a one for vascular capillaries and arterioles, tubular cytoplasm, and so forth. And if you start collecting now definitions of all the spatial area of histology, you can then put them through a simple k-means classifier that will cluster them in k-space, high-dimensional space, and then distill them down to a small number of spatial definitions, kind of like that handwriting example. We use as a definitional a default 16 spaces, but you can use more or less. So we end up in this high dimensional space, which is, for just convenience purposes, projected here on a 2 space. And now the images come back at every pixel now. Yes, there's a color. The color means nothing optically. The color is the biological definition. And you can apply this because we have fast computers with GPUs at high computational scale and start defining now entire surface areas, whole slide images or libraries of whole slide images in terms of this new color space, which is really a definitional space. And this is the so-called feature engineering, where we create libraries with this tool by identifying basement membrane or glomerular tissue or nuclei. And in very short order, the tool converts that from color pixels into definitional or biological context pixels. So I'm going to go through a couple examples where this tool has been used for a clinical production workflow. One is simple micrometastasis. If you think about in your GI large service, some time is spent looking at lymph nodes for micromets. It's not super slow, but it's not the fastest process in the world. Imagine a workflow in which all the whole slides you're looking for digitally for a colectomy case for cancer, and you have to stage it, have had the full surface area pre-screened, at least on the nodes, but you probably look everywhere for micromets, and flagged all the locations in the nodes that had micromets. So then you're confirming as opposed to searching for it. That's faster, right? Doesn't mean you can't, that you don't have to look at the rest of the case, but at least it helps you identify that if you have a case with very, very small micromets, you don't at least miss them. And we know this is important. If we look, for example, and this is just the standard staging for colonic carcinoma, the node pattern makes a significant difference in survival. So you really want to do an accurate job on this because this is predictive of outcome. So that accurate information is useful. Now, this is where the big box software sometimes fails, though. Let's say that you have an adenocarcinoma with a solid variant, so-called medullary or the MSI type, or the significant inflammatory response that makes it difficult to find, but for the algorithm's sake, in the primary lesion. And then it looks in a slightly different morphology in lymph nodes. Your big box algorithm that the vendor made may not recognize this algorithm or this variant of malignant cells, as well as the usual type, in which case then you need a workflow where you can say, and this has to be real time because you can't let these tools slow you down. This is the morphology I'm dealing with from the primary, and then apply it to all the lymph nodes and tell me if I've got any micromets. So this is a video that would show that hypothetical workflow. This is actually, the only difference here is I'm using the lesion in the lymph node itself, just defining a section of nucleus and surrounding cytoplasm. And then the algorithm will take that to find similar areas. This is going to a GPU core. This is all real time. And you'll see that it's going to avoid the lymphoid germinal centers and finds the micromets for you. So the only difference in a production workflow would be you would pull this from the primary and apply it to all the whole slide images, with the notion being this is an unusual variation on the epithelial lesion, and you want to make sure that you're using this particular cell as opposed to whatever is in the thing that was pre-baked by the vendor. So this is an example, and there's another field of view doing the same thing, picking a representative malignant cell in its nucleus. Nothing too fancy there. Submitting it to the engine, real time. It should identify, of course, the lesion of interest. It's, you even see it's avoiding some areas within that because they're probably not malignant cells. They're either capillaries or blood or connective tissue or vasculature. Example 2.
In the first example, it was even pointing out isolated tumor cells. So isolated tumor cells, as you know, here. Some here, something in the subcapsular sinus that probably we would miss. I would miss it. And yeah, this cluster, I don't know what this cluster is, but,
Oops, yeah.
but that the computer is defining this as an ITC. ITCs are a big deal now in endometrial cancer. The one even on top. I mean, this for I think I can do this, but I don't think I will do this.
Well, we need to be careful though. Just because it's circling it doesn't mean it's right, too.
It needs to be looked
But it needs to be looked at. So, I mean, this would say, okay, well, if we really want to know, we could do an immunostain. But I think the concern, though, from a workflow perspective, you just missed the whole fact, because if they're just in the subcapsular sinus, it's really easy to miss. And not so easy to miss if you do a special stain, but if you don't do IPOX and you're just doing H&E, this is what I think of like a safety net, right? Again, it's not replacing you, but it's making sure you look at it. So this is the kind of thing they think will change practice from screening to directed review, which is a good thing. The gist. Now, so this example, because we had this in our library, is a osteosarc, but you can just imagine that you're looking at a gist instead in 50 high power fields. And we'll make it a little bit more complex. This is a gist that had weird mitotic figures, at least weird from the perspective of what was in the library. So if you just use the big box software from the vendor, it wouldn't work so well. So this is a case where you want to run the software and then use that real-time workflow to generate a classifier based on what you've got at hand. Because you can spend some moments and find the mitotic figures in anything, right? That's not the problem. The problem is finding all of them and then giving you the count. But the trick is to do this accurately and still do it in 2 minutes as opposed to 45 or 20. And this is a 2-minute video that'll show that. And of course, this is the updated NIH score for GIST. You can see there are quite a few rules in terms of the plus the 50 high power fields. And is it less than 5, 6 to 10, or more than 5 or more than 10? The computer can memorize all this and apply these rules for you and give you immediately the overall risk score. So that's another plus of having it be computational. In terms of the workflow, it turns out to be really easy, and it does not take the pathologist out of the loop, which I think is really critical. So in this case, this osteosarc, I'm going to select one of the weird mitotic figures. Maybe it's not that weird, but for the library that we had, it was. So I'm painting it. This is how this algorithm works, submitting it to the engine. And the engine now is in a slightly different mode. It's not going to call them directly. It's going to color map them with a circle based on its confidence level, and which is a heat map. And then the pathologist can up call or down call them. And as you up call them by clicking on them, you notice the count starts increasing. So now this is exactly what I meant by directed review, because it's much easier to see them once you've got a circle around them, right? And this is the next field of view. Again, and we're waiting, and then that's an example of one. Let's see if let's see if it finds that one. The engine is running. This again, these are real time. And look at the one that I thought was really a hot heat mapped is red. We'll count that one. We're counting a few more. Some are not. So again, because you've designed it to be sensitive, not specific. And that's where the pathologist comes in. You can look at them and say, no, that's really not a mitotic figure. But now the process is much faster. And the other thing is, since it's a whole slide image, it's mindful of where it is in the image and doesn't allow overlap. So your 50 high power fields are not overlapping or touching each other. So it's a clean acquisition from the slide. And you can see now very quickly, we've gone through just a very, a few high power fields, but much more streamlined. And again, this software is by no means optimized. This could be even further improved. But this is the kind of tool we'll be using in the not too distant future for something as mundane as mitotic figure counting. And you see, it doesn't remove the pathologist from the equation. It's quite the opposite. It inserts your expertise in defining what the baseline morphology is for a given image. This is work that we've done with Laura Barsoni, a little bit more on the research side. We picked a very difficult feature to see if we could classify, which is the subtubular vacuolization of early injury and repair of tubules. And after just a very small number, normally for a pipeline, you'd never use this few features of 8 positive, 8 negative features. So this is by no means, ready for production. But still, it found the subnuclear vacuoles with very high affinity. I couldn't have painted those as accurately as the algorithm has identified. So it's just the pilot data, and this is the ROC curve, which is very, very good compared to the ground truth map that we manually generated with an AUC over 0.9. So the preliminary data from these types of algorithms really suggests that not only can you build a tool that does real-time classification, but you can put it in a pathologist's hands and have very satisfactory outcomes in the setting of a real-time sign-out workflow. Oops. Uh-oh. Have a paper towel or something? Maybe spilled water on it. Should be okay. That was bad. Let me see. They say this laptop is waterproof, so. Oh, that's great. There you go. Oh, great. Sorry about that. We'll see how good their waterproofing is now, right? There you go. There you go. No worries. There you go. Previous. Okay, so next one, IBD assessment. This is a whole slide image. I'm going to focus in on one area, which is there. And through using just a series of classifiers, and I'll go through the algorithm in a little bit, it's possible on the fly to make an algorithm that will identify areas of interest to the pathologist. For example, I train this to identify eroded, the areas of erosion of IBD versus areas that are not so eroded. And the question is, can you make something that's exquisitely sensitive enough that you can now quantify erosive architecture throughout a whole slide image? So that architecture will start with the sample training image, the original tile. We generate a family of our biological contexts, so epithelium, the crypt, inflammatory cells, mucus on the surface, lymphocytes, polys. And each one of those features then gets thrown into a machine learning classifier that generates a raw classification, because k-means, for example, randomly assigns color, which then needs to be further adjudicated. And that can happen very, very quickly. This is the algorithm that I'll show you. This is Viper at work. So the original image after classification, that's the raw classification. After the clusters are defined, we have now every feature in the image. So you can see, for example, the mucin in the epithelium is one color. The epithelial areas are another color. And these yellow areas correspond to the worst areas of erosion. But if you remap this just with the colors of interest, you can identify then the worst areas of erosive injury and generate all the types of images that you need for image analysis. For example, just false color, or just all of them combined together into single color overlay or a binary mask. But most importantly, the goal is to allow the pathologist to generate a classifier on the fly, with the heat maps then being used by other potential image analysis software. So this is the full field of view that we had used initially. And after processing, you can see now it gives you, it's like an IPOC stain, but it's not a real stain, it's a computational stain. And those are the areas that by machine learning matched to the worst areas of erosive architecture. Is it perfect? No, but again, that was trained on a small number of fields of view. As these pipelines get optimized, there's really no limit to the number of computational stains we can have in our armamentarium to help us look at what has historically been conventional histology and then superimpose on that computational knowledge of morphology. In other words, the yellow areas are yellow because of their biological context structurally, not because of the color of the original pixels. This is a similar exercise on a wide field of renal biopsy. As I go to the next field, you can see that it's changed in color. Again, the colors are not stains, they're biological meaning, but only after magnifying in a tremendous amount do you realize This is taking place at the pixel level. There's no graduate student or postdoc in the world that would be willing to classify this image at the pixel level. We actually did the math. One of these whole slide images at the pixel level in 16 classes like this would take 26 years. So it's just not going to happen. This is a Swiss roll of an IBD model. So I promised I'd show something with IBD as well. And we can look at, when you zoom in at various areas of health have a fundamentally different pattern in this biological context space than diseased areas. And it's possible now to classify disease by the constellation of the constitutive component vectors in this biological context space. So this is the actual tool itself. This is Viper. I have it running. Hopefully my machine doesn't die from water before we go there. And I've already loaded, this is an esophageal biopsy, whole slide images in here. And this is actually the margin of the lesion into the deep adventitia. And I've created a classifier ahead of time that's designed to identify the invasive component, which is red circling yellow. That's how I've done that is really not as important as the fact that those are the colors I've chosen to be the payload. The payload is the invasive margin. And then when we look at this type of histology from the prism of what it means biologically, and we could apply this algorithm now to a larger field of view, this is what H&E looks like. We're perfectly comfortable saying that it looks invasive, but why not superimpose on that the computationally extracted meaning of invasiveness, and we'll see where the invasiveness is. And that gives a whole new light to invasion. You can see there's little islands of invasion up top where you have single cell nests, and then you have areas throughout. So I mean, there's many, many ways that this type of data can re-render or represent what is routine histology. But that doesn't stop there, because then when you superimpose other classes of data like genomics or transcriptomics, the amount of information you have is truly overwhelming. So let's go to the next slide. So just very briefly, once you have a definition of every pixel in terms of its biological context, you can make really elegant educational tools. You'll notice on the cartoon on the right, areas light up as you hover over them because you know what they are biologically. That's a use. So you could take whole slide images and then map them to educational tools, which is kind of a nice byproduct of this architecture. And then finally, where things are really headed, this is still in the realm of research, but this is very quickly becoming clinical, to take histology, this is frozen tissue, and place it on the Visium platform, which are these 40 micron circles. You can sort of make them out as little gray circles in a hexagonal pattern. Each one of those has 2,500 transcriptomic barcoded features, which can be superimposed and captured and analyzed. But in tandem, we can analyze the image morphologically. In this case, I was looking for anything epithelial versus anything vascular, and you can see the medullary rays have mapped out morphologically. And then for every given location, to essentially make a pie chart of the constituent components from an expression perspective at that location. This is relatively coarse still, but as the feature size decreases, and the new version is just being tested now, our colleagues, Michael Eden at Indiana, are doing this. We will have 1 and 2 micron pitch data sets. We'll be able to see the molecular trajectory of cells at the near cellular level, which I think will give an incredible level of insight when you superimpose that with morphology. And then finally, when you take that high precision data and apply it in forward setting, you can literally, oops, let me make sure this video works. Here we are. By selecting various genes, which have been spatially coupled with the morphology, we can identify where they're expressed. And that's a new window into histology that's not been available to pathology. And it's information overload, right? This will take a while to absorb how to most effectively use this, but this is where histology is headed. So I think I hope to just excite you that histology is not dead. It's I think undergoing a second wind. And the inverse is possible as well, where you can identify regions of interest and then submit them to the engine and then identify the affected genes in those areas. So in summary, I think AP sign-out workflow really has the opportunity for utilizing morphologic data in many new ways for interrogation with concurrent analysis of the other classes of data, the transcriptomics, the omics, the clinical data, and especially the single cell and transcriptomic data that's coming down the pike very quickly. And by using augmented segmentation like I've shown you, the capabilities will be increasingly important for machine learning, tools that pathologists can use on the fly. And again, shifting what biology is from optical information to biologic potential of disease. And I think that makes it appropriate to consider for deployment in clinical use. And then finally, the big box problem with AI can be solved by at least providing some tools that can be used directly for pathologists to make custom or bespoke algorithms as needed on the fly. And these new classes of tools, I think, were allowed for the transition of pathology workflow as it is now from being screening to being directed review. And I hope this elevates our practice of pathology. And I'd like to just acknowledge my colleagues at Michigan, Duke, Iowa, Oklahoma, and City of Hope. Thanks so much.
Thank you for that excellent talk. I had not known much about this space before one of the hematopathologists approached me and asked me to quantify fibrosis within bone marrow cores for MDS, and I stumbled upon QPath, which I'm sure you're also well aware of.
Yes.
And then found that relatively easily I was able to train a pixel classifier, and it seems very similar to this. Have you compared your Viper? I looked for Viper just now on GitHub. I don't know if it's
the earlier generation is available. It's SIVQ. We're just getting this out.
Oh, I see.
So
Okay.
if you look at spatially invariant vector quantization, that's the back-end engine to this.
I see. Okay. Because I was interested because it seems like QPath has a lot of these similar functionalities.
Similar.
But I don't know if it has the ability to put omics on top of.
It doesn't. So this is very similar to QPath.
Okay.
With the added, the main difference is it has the k-means and the XGBoost and other support vector engines built into it.
Okay. Okay.
Thank
you.
Thank you very much. Oh, that was amazing. I was trying to stay glued to my seat. Many times I was going to say, well, you know. So my question is this. I see that you're collaborating with Duke, with Laura, which is the kidney, which is one of the exciting points. So I think my question is on behalf of the GI people in this room. Now you've planted a lot of ideas in our minds. And now we are waking up at 2 a.m. thinking of what we could do. I'm not thinking we'll wake you up at 2 a.m. But as soon as we wake up at 6 o'clock, and we'd like to share with you. So is there any structured way of collaborating, or just being able to tap into some of these things that you are doing?
Yes.
Okay.
Yeah.
So,
Absolutely.
So can you tell us how specifically?
No, we're looking for collaborating groups. We have several at this point, and more is wonderful. Because what that allows us is to get feedback on how the tool works and how to make it better. So we need users.
Thanks so much for that wonderful talk. I'm really curious, as it sounds like, your field is completely rethinking how AP sign out might go out. Is there corresponding exciting work in how the histology process works? So much of this seems probably be currently constrained by little sections. Even for example, with biopsies today, you could see with this workflow in the future, instead of just having 2 or 3 sections, being able to put it all in or use it differently when you know that you might not need to conserve as much for, traditional molecular staining. And also I just kind of imagine a scenario where you could just take an organ and kind of like run it through a slicer and put the entire thing through and scan it. So I'm just curious. I don't know anything about that.
So that's not the focus of our group, but there are several groups, well, at least several. So at the University of Washington, Seattle, Jonathan Liu has developed a very fast so-called open top light sheet microscopy that uses clearing agents. I believe the one he's found that works the best is cinnamon oil. That computates, so there's no stain involved, like there's no H&E, but by computationally looking at the equivalents, can generate an H&E image from this cleared tissue at the diffraction quarter micron limit. And the stepping size is actually smaller than the diffraction limit. And it goes, so it's volumetric data. So the problem with those whole slide images, we've been playing around with some of his data sets, they're huge. So one of his images fills up an entire multi-terabyte hard disk. So, it's an embarrassment of riches. So that's one technology that's very promising because you don't have to, it's non-destructive. The tissue basically has a clearing agent, which is reversible. It's imaged from the surface, but gets very, very deep penetration, 15, 20 microns, which is for many types of aspects useful. And they're working on 100 microns at this point. Richard Levinson at UC Davis has Muse, which again is another technology using LED fluorescence for directly transilluminating the surface of tissue, no section being cut, and the resolution is microscopic. It looks just like a histology section in H&E. They use, again, color conversion to convert the UV light and the polarization information and the way the structural illumination works into something that looks just like an H&E slide. It's amazing. And then there's Özkan Aydoğan at UCLA, who has a technology that uses like cell phones or very low resolution cameras and reconstructs phase and gets super resolution microscopy. So if like in a low and middle income, low setting where you only have cell phones, you can generate oil immersion quality peripheral blood images from just the pictures taken on a cell phone with an adapter. So that's just a cross section of things going on with really advanced optics. So that's happening. And the question is, how long does it take for those to be translated to commercial products that can be either used by our labs or in low and middle income countries? And I don't know. They're working on it though. But there's a lot of really exciting stuff going on in advanced optics that can do things without a slide. So you're right. It may be the case in 10 years, we'll have all these algorithms, but we won't be applying them to slides. We'll be applying them to images that were extracted directly from tissue. It's a great question.
Thank you so much. That was really intriguing. I'm an aberration in this room because I'm not a GI pathologist, but I'm an ex-renal pathologist. And I was particularly intrigued because I've been working for a long time to get pathologists to stop using the term acute tubular necrosis, because in fact, most of the time when patients have acute kidney injury, from a clinical point of view, the tubules aren't actually necrotic, but they're injured. And it looks like this technology has an ability to really identify tubules that have enough injury to produce the clinical acute kidney injury concept, but are not necrotic. Is that correct?
Yes, in essence, we were using that algorithm not as much to identify the biology, but to identify if the algorithm could identify a hypothesized target. But from separate efforts within the Kidney Precision Medicine Project, what we're finding is acute kidney injury and chronic kidney disease are continua of the same process. And it's not entirely novel, but what's interesting is the evolutionary pathway. And by having now time series biopsies on patients that we've never had before, we're learning about what that chronicity looks like. And it's actually targeting a number of opportunity targets that we've not considered before. So it's very exciting. So I think if nothing else, the KPMP project will allow for new insights into what chronic kidney disease and acute kidney injury are, which may be really the same thing.
I was having similar thoughts, John, as I was looking at some of these lesions, and I can see that, oh my God, the computer is going to actually teach us things in transition, because you can see the computer may be picking up stuff that we don't have names for them now. I always tell our residents, be merciful, be gentle with us later on, because you will look back and say, oh my God, these guys were so crude. We could only tell cancer when it hits you in the face, but what if these algorithms are going to be picking things in transition, just as you mentioned? I think they will be tasked in trying to find the significance, the biology, the terminology, the whole. You can see how this is taking our practice in the future.
Yeah, just as a final closing thought, since each pixel in the image is classified, the pathologist has full control over which pixels to display and not display. So I can turn off all the background stroma, for example, and regenerate this image interactively. You can see now this could be applied to the whole slide image. If I want to get rid of the nuclei, I could turn this feature off. And now you can superimpose it on the original image. And you can see now how these features relate to the original histology. So there's a number of ways this application can help the pathologist visualize where these computational structures live with respect to the morphologic structures. We're just tapping the beginning of this. But and this is, again, you mentioned QPath, which is a great example. That's another very powerful tool for creating automated segmentation. And the real finesse with this will be finding ways to take those tools and responsibly deploy them in the clinical setting. And that's what my group is primarily focused on, creating clinically deployed tools. And we specifically set out not to make them commercial entities. So, I mean, possibly companies will take the source code, which is under GPU, a GNU license, and repurpose it. But the intent now is collaborative, to share these as much as we can.
Thank you. Any further comments or questions?
The repository is on our, we have a Dropbox site, but we need to put it in GitHub. Yeah.
All right. Thank you. Thank you, Dr.
Thank
Davis.
you.